Since its launch in late 2021, JWST has been making leaps and bounds in our understanding of space, from planets to galaxies to even large-scale structure. Among its most famous discoveries are huge galaxies that are much more massive than we expect for how old they are, so much so that they seemingly break our current model of cosmology. However, mass is one of the most difficult properties to measure from astronomical observations, and it often requires several sets of assumptions to all hold true for any given galaxy. One way to estimate the mass of a galaxy is through spectral energy distribution, or SED fitting. Using observations of the galaxy from different wavelengths, we can model the full distribution of light for the galaxy. Because the optical and infrared light is proportional to the stellar mass of the galaxy, we can then use the SED to calculate the galaxy's stellar mass. Something that can affect the SED fitting is the presence of nebular lines. These are emitted from clouds of ionized hydrogen called H2 regions, and they're typically found in star-forming molecular clouds. Some examples of these H2 regions are 30 Doradus in the Large Magellanic Clouds and the Orion Nebula in our own galaxy. The nebular lines then show up in the SEDs and affect the mass estimates. These lines are particularly impactful since they're right in the wavelength range that is used to calculate the stellar mass. So the question then becomes, to what extent do these nebular lines impact the SED-derived galaxy masses? My name is Grace Krahm. I'm a senior at Agnes Scott College, and this is what I worked on this summer with Deshika Narayanan at the University of Florida. In order to quantify the contribution of nebular lines to the mass estimates, I took simulated galaxies from the SIMBA hydrodynamical simulation at several snapshots across the age of the universe, starting at redshift 10, or about 500 million years after the Big Bang, and ending at redshift 0, or present day. For each simulated galaxy, we first used the Powderday radiative transfer code to ask all of the stars in the galaxy to emit light in several different wavelengths, which we can then use to construct a mock SED. Then, we used the Prospector SED fitting tool to create observations that could result in said mock SED. We can then proceed as an observer would and fit an SED to these observations and therefore calculate the galaxy's stellar mass. To incorporate nebular lines, we simply add the nebular lines to the Powderday mock SED and then proceed the exact same as before. Just looking at present-day galaxies at redshift 0, we can already start to see that the presence of nebular lines results in consistently higher mass estimates. The extent of this difference depends on both the number and brightness of the nebular lines present, ranging from a few dimmed lines to several brighter lines. This difference in mass becomes even more pronounced in galaxies with more star formation at higher redshifts. Once again, we have the redshift 0 galaxies with an average contribution of 9% mass from nebular lines. This increases as we continue to look galaxies further and further away, with 10% at redshift 2, 17% at redshift 4, 22% at redshift 6, and 73% at redshift 8. This tells us that nebular lines do in fact contribute a significant amount of flux to galaxy SEDs that can then change the mass estimates, and as redshift increases, so does the contribution of nebular lines, which means that many of these early massive galaxies that JWST has been finding could have very overestimated masses.